Hi, in this lesson, we're going to learn about the primary trig ratios in standard position. Now, the primary trig ratios are sine theta, cos theta, and tan theta. There are actually other trig ratios that you'll learn about in the future, but we're going to focus on these ones right now. We've already talked about standard position, which was defined by a point P, a fixed distance from a fixed point, and moving counterclockwise positive or clockwise negative. This leads to a new definition rather than SOHCAHTOA, where we can say now that the sine of theta is the y-coordinate over r, the cosine of theta is the x-coordinate over r, and the tan of theta is the y-coordinate divided by the x-coordinate. So we're going to rely on references to x, y, and r rather than opposite hypotenuse and adjacent. Now remember, r is always greater than 0, therefore always positive. We're going to keep that in mind. Also, sometimes in a unit circle, actually all the time in a unit circle, r equals 1. Sometimes we refer to a unit circle is what I meant to say. In this case, the sine of theta would merely be the y-coordinate, and the cos of theta would merely be the x-coordinate because the r values would be 1. Tan theta is unaffected. So keep that in mind. Sometimes we refer to y over r, sometimes we just refer to y or x over r and x. With this in mind, remember previously that we talked about the symmetry in standard position, how an angle theta represented by reference angles in each of the 4 quadrants and 4 corresponding standard position points have all got the same values of x and y, but only their signs will change. In quadrant 1, both x and y would be positive. R is always positive. As a result, because of our new definition, right at the top of the screen there, the sine of theta would be the y over the r value, so it would be positive. Cosine is x over r, therefore positive, and tan, y over x, or positive. That's what you're used to from SOHCAHTOA and acute angled triangle referenced trigonometry. In standard position, though, we can talk about obtuse and reflex angles, coterminal angles, negative angles, and so on. And so this standard position referencing is going to help us, but we have to keep track of the signage. In quadrant 2, x is negative. Y and r stay positive, therefore the sine of the angle theta would remain positive. But cosine is now negative, and tangent, because it refers to x, is also negative. Maybe pause at this moment and try filling out row 3 yourself and see if you can understand what's going on with these signs, and then rejoin me. Alright, hopefully you got these signs. Both x and y are negative, leading to both sine and cos being negative, but now tangent, because it's the quotient of x and y, is actually positive. Pause again and fill in the 4th quadrant, and again rejoin me and check your work. In quadrant 4, the signs across the chart alternate. X is now positive while y is negative. R is always positive, sine negative, cos positive, and tan negative. Now, sometimes people refer to this as the cast rule. It's just a way to keep track of signs. Notice that in quadrant 1, all are positive. In quadrant 2, only the S is positive. In quadrant 3, the T, and in quadrant 4, the C. So if I started in quadrant 4, I could say C-A-S-T, or cast, for what remains positive. Other people refer to this from quadrant 1 and say all students take calculus or something like that to keep track of the signs. I don't actually like either of them. I just like to reason it out based on the definitions, but I present it for you in case that's helpful. I've got 2 examples now about applying these new definitions for sine, cos, and tangent in standard position in a context. Here's the first example. We're given a point P, negative 3, 4, that is on the terminal arm of an angle theta in standard position. So negative 3, 4 would put it in quadrant 2 like this. So let's draw a standard position angle showing the direction theta counterclockwise and the point P with coordinates negative 3, 4. So that means I've got a 4 here, I've got a negative 3 here. Hopefully you can see right away from Pythagorean theorem, because I'll always get little right triangles here with the coordinate system, that the r value is going to be 4 and negative 3 squared rooted, or 5. That leads me to being able to come up with trig ratios for sine, cos, and tan. Sine theta is the y-coordinate, 4 over r. Cos theta is the x-coordinate over r. And tan theta is the y-coordinate over the x-coordinate. And we bring the negative sign to the top by convention. Now, to find theta, something tricky is going to happen. We're going to get our calculators out, and I want to show you something. This is probably the trickiest part of what's going on here. Let's get your calculator out. What I'd actually like you to do is pause in a moment, and I'd like you to make sure you're in degree mode, and then check what the angle is using sine, what the angle is using cos, and what the angle is using tangent. And we're going to have to do arc functions, which means the inverse function. Okay, so a second function button. So try those out and then rejoin me. Okay, what we actually get appear to be 3 different results. We get 53 degrees when I do arc sine, or the second function of sine, 127 degrees when I do arc cos, and negative 53 when I do tangent. Well, looking at the original diagram in standard position, we see that it can't be 53 degrees because it's in quadrant 2. It also can't be negative 53 degrees. That'd be in quadrant 4. I really need this answer here, 127 degrees. What's going on is that the signage is resulting in the smallest angle possible as a result, and there could be more than one location that has this ratio. Think about it. When I have sine with 4 and 5, y and r, that can occur in quadrant 1 or 2. A cosine that's negative can occur in quadrant 2 or 3, and a tangent that's negative could occur in quadrant 2 or 4. Your calculator is going to give the very smallest number that it can as a result, and thus for the sine it gives a quadrant 1 answer, for cos it gives the quadrant 2 answer, and for tangent it gives the negative quadrant 4 answer. So we need to interpret this in our context and recognize that what we have is a reference angle of 53 degrees that is in quadrant 2. And so theta is 180 minus 53, or 127 degrees, which is the answer given by the arc cos function. But you're going to have to think about it each time. Okay, we're going to do another example, and it's also going to have this angle issue in it. So I want you to think about this. You might want to pause and try this again, or work those answers on your calculator before we move on. Here's the second example. We're given an angle in standard position in quadrant 3. We're told that the cos of the angle is negative 12/13, and therefore we want sine, tan, and theta. Okay, remember that sine theta is an x-coordinate over an r-coordinate, and that's negative 12 over 13. So the x is nearly as large as the r. Well, the r is fixed in the diagram. It's the radius that I have, and so I need to draw something that's round about here, I would say. Negative 12 for x, 13 for y, and there for r rather, and there's your y-coordinate. Now we're going to figure out the y-coordinate. So why don't you pause and do that? And actually, I'm going to get you to try to work through this whole problem from this point, having given you that hint in the diagram. See if you can figure out sine, tan, and theta, then rejoin me. All right, let's see how you did. To solve for the unknown side, I need hypotenuse squared minus the other side squared, so it's 5. But it's in quadrant 3, so I need a negative. Don't forget that. You'll have to put that in. As a result, the sine of the angle being y over r is negative 5 over 13. Tangent, a negative divide negative, so 5 over 12. And putting them all into the calculator, again, observe that we get 3 different results. It's definitely not a negative angle in quadrant 4. It's definitely not a positive angle in quadrant 1. 157 is also incorrect because that would put it in quadrant 2. So actually, none of these is giving the correct angle in quadrant 3. What I need to do with this information is recognize that they're telling me in their way that the reference angle is 22.6 or 23 degrees, but it's in quadrant 3. So theta is 180 plus 23 or 203 degrees, and your calculator does not provide that answer. Kind of disappointing, isn't it? All right, well, that's the basics of how sine, cos, and tangent in standard position work, how to use your calculator with it, how to draw diagrams in standard position and pull information from that. Hopefully this is going to be helpful to get you working through various problems on this topic. Good luck.